Now the next element is inductor. So the inductor, it will store energy in magnetic field. What happened in case of capacitor? It stored energy in the electric field. Inductor is, it will store energy in the magnetic field. Now what does the inductor look like? It is nothing but a wire which is wound into a coil. Okay, so this is the coil, and the material on which it is wound, this is called as the core, and the core is usually a magnetic material. Okay, and sometimes it can simply be air cored. That means there is nothing, it is not wound on anything, it is simply wound into a coil. The wire is simply wound into a coil. Okay, now when the current flows into this coil, then the magnetic field, what will be the form of the magnetic field? It is going to be like this. Okay, so this you can visualize if you consider a straight line, and if current is flowing through this, then you apply the right hand thumb rule to find the magnetic field direction, right? So what is the right hand thumb rule? You have to curl your fingers around the wire in such a way that the thumb is pointing to the direction of the current. Okay, so that means this is the thumb and this is the direction of the four fingers. Okay, now what is the direction of fingers? That will be the direction of the magnetic field. Okay, so if you consider a top view, let us say the current is flowing out of the plane. Okay, now if you apply the thumb rule, then the magnetic field direction, it is going to be in the counterclockwise sense. That is the direction in which your fingers will curl around the conductor. And what about, this is current coming out of the plane. What about current going into the plane? In this case, the current direction is going to be just opposite, which is clockwise. Okay, so in a similar manner, for each turn, if you are applying the thumb rule, then this is the resulting shape of the magnetic field. Then what about the direction? If for each turn you are applying the direction, then this is the direction you are going to get. Another simpler way, whenever there is a coil, another simpler way is present where you can find the direction of magnetic field. So what is that is, you have to wound your fingers in the direction of the current through the coil. Okay, so if you do that, then the direction of the thumb will give you the direction of magnetic field. So now if you are wounding your finger, you're curling your fingers in the direction of current, then your right hand thumb will point in this direction. Okay, so this is the direction. Okay, what if the coil was having current in the opposite direction, or the sense of winding is different? See here, in one case I am taking current in the opposite direction like this. Okay, so now if you wound your right hand fingers in this way in the direction of the current, then the magnetic field is going to be just the opposite. Okay, and in another case, here I will take the same current direction but a different sense of winding. Okay, so in the first case, if you can see, the current is flowing from this terminal and coming out from this. Here also, if I take the current flowing into this terminal and coming out of this, but here the sense of winding, you see, the coil is going from behind the core. Okay, so here what will be the direction? This is going to be the direction. Now if you apply the right hand rule, then the magnetic field shape is going to be the same for any coil, but now the direction of the right hand thumb, when you curl your fingers, it will be in this direction. Okay, so the sense of winding, the direction of current, both are going to affect the direction of magnetic field. This is a basic concept that you will be needing to understand transformers. Okay, so if you can understand here itself, then while discussing transformers, it will become easier to you. Now we will see the VI relationship. So the inductor, it is represented like this. Now the voltage across it, if you take as V of t, and the current is I of t. Now what is this VI relationship? The VI relationship is V of t is equal to L times di by dt. Okay, and this L is the inductance and its unit is Henry. Now the inductance is going to depend on that particular coil. So let us first take the core, and on this core the coil is wound, let us say. Okay, Now what is the inductance of this particular coil? It is given by L is equal to mu n square A by L. Okay, so now we will see what each of these terms mean. First, if you see mu, this is the permeability of the core. The coil is wound on a core, right? So the permeability of that core is mu. It is given by mu naught into mu r. What is mu naught? It is the permeability of free space. So that means if there is no core, or you can say the coil is simply wound in the air itself, then mu is simply equal to mu naught. And what is mu r? This is the relative permeability of the material. So for air, it is going to be 1. Okay. Next, what is N? This is the number of turns of the coil. Okay. Next, A is the area of cross section of the core on which it is wound. Okay. So that means this area what we have here, that area of cross section is going to be A. Okay. And finally L. L is the length of coil. So that means this distance. This is L. Okay. So this is how we find out the inductance of a particular coil. Now what is the sense of inductance? That means, for example, if you consider a resistance, the resistance gives a measure of how it is opposing the flow of current. So you can write opposition offered to flow of current. And what about capacitance? A capacitor will give you a measure of how much it can store charge. A particular capacitor, how much it can store charge, right? So it is the charge storage capacity. So now what is inductance? In the same lines. So it will give you a measure of how much it is opposing the change in current. Okay. So opposition offered to change in current. So this is the physical sense of what an inductance means. Now we have seen that the voltage is equal to L di by dt. Now we want to express I in terms of voltage. Okay. So V of t is equal to L di by dt. This implies that if you integrate on both sides, then I of t you're going to get 1 by L integral V of t dt. Okay. So if you are not considering the initial values, then you will consider the initial value of current, or you can write 1 by L integral some initial time to the required time. Okay. So if you are writing the limits, then you don't have to worry about the constant. Okay. So this is how you express current in terms of the voltage. Next, power and energy. So power is pretty straightforward, and from power you can get the energy, right? So what is P of t? Instantaneous power is equal to V of t into I of t. So V, if you replace by L di by dt, then you're going to get L into I di by dt. Now from here, energy you can get as integral P dt from a particular time, initial time t naught if you take, to the time t. Okay. So then what you're going to get, integral t naught to t L di by dt into I into dt. So this will leave you with t naught to t L I di. So what you're going to get, the final answer is L I of t square minus half L I of t naught square. And if the initial current is 0, if initially there is no current flowing, then this term will become 0, then energy will simply be equal to half Li square. Then energy is equal to half Li square. Now just like in the case of capacitor, you will have some important properties of the inductor as well. So the first one is it will act like a short circuit to DC. In the case of capacitor, it was open circuit, right? Because there I is equal to C dV by dt. So if there is a DC voltage, then I will be 0. Okay. So now what about here? In this case, V is equal to L di by dt. Okay. Here voltage is equal to differentiation of current. So if there is a DC value, then if I is DC value, then di by dt is equal to 0. This means V is equal to 0. So V is equal to 0 means short circuit. Okay. Now remember, this is at steady state. In transient state, it is going to be different. We will discuss that in transients. Now, the second point is, in the case of capacitor, voltage could not be changed abruptly. Here, the same will apply to the current. Okay, current cannot change abruptly. So why is this the case? It has a similar reasoning like the capacitor. V is equal to L di by dt. Abrupt change means that dt is tending to 0. Okay. So when dt tends to 0, then this entire term will tend to infinity. So that means an infinite voltage is required for the current to change abruptly, which is why this cannot happen practically. Okay. So infinite voltage is required for current to change abruptly, which is practically not possible, or which is not practical. Okay. And finally, the third one is, it's not exactly a property, the practical inductor, how it will be like, how it is represented. So the practical inductor will have an ideal resistor in series with a resistance. Okay. So where does the resistance come from? In capacitor, the resistance was taken parallelly. Okay. Here we are taking in series. So why is that? What is the difference? See, remember, one thing you have to understand, practical means that it's not that there are two elements in series. We are modeling. Okay. Remember this word modeling. We are modeling the behavior with an appropriate circuit diagram. Okay. So here what is happening, the inductor is finally a conductor only, right? And any conductor will have some resistance. So when a current is flowing through the inductor, then it will experience some resistance, right? So it is in the same path of the direction. So that is why we take in the series. So the behavior of the voltage and the current is in such a way that this is the correct way in which we can model the particular inductor. Okay. Now sometimes they might say that there is a stray capacitance as well. That means a parallel, the inductor will behave in such a way that there is a capacitor across it. Okay. So this is not very important. This is the main practical inductor that we often consider. Let's now do a simple question. The voltage across 2 Henry inductor is V of t is equal to 10 times 1 minus t. Find current flowing through it at t is equal to 4 seconds and energy stored in it at t is equal to 4 seconds. Initial value of current through it is 2 amperes. So you can pause the video and you can solve first for yourselves, then you can see the solution. Okay. So what is the given information? V of t is equal to 10 times 1 minus t. And now we have to find the current at t is equal to 4 seconds and also the energy at t is equal to 4 seconds. Okay. And what else is given? The initial current. So if the initial time, if you are taking as t naught, then initial current is 2 amperes. Okay. So now what is the current? The current is given by current I of t is equal to 1 by L times V t dt. Okay. And if you take the initial value, then you don't have to take the limits. Okay. So what you're going to get here, inductance is given as 2 Henry. So 1 by 2 integral 10 times 1 minus t dt plus 2. So this you're going to get as 5 times t minus t square by 2 plus 2. Now you can simply substitute t is equal to 4, and the final answer I'm telling you is minus 18 amperes. Now what about energy? So the energy we need at t is equal to 4 seconds. So what is this? Half L I at t is equal to 4 whole square minus half L initial value of current whole square. Okay. So this is given by half into L. Half L you can take out common. So 1 by 2 into 4. Now at t is equal to 4 we have found out current is 18 amperes. So 18 square minus the initial current is 2 amperes, so 2 square. Okay. So this if you calculate you're going to get 324 joules. Now what about equivalent combinations of inductors when they are placed in series and in parallel? First we will consider the parallel connection. Okay. So here we have inductors, let us say L1, L2 and so on till Ln, and the voltage across the entire branch we will take as V, the current through this we will take as I, and each of the voltages, the voltage we can take as V1, V2 and so on till Vn. Okay. So now if you apply KVL, then what is V? It is equal to V1 plus V2 plus so on till Vn. Okay. So this will give you L equivalent di by dt. This is the required equivalent value of inductance. Di by dt is equal to L1 di by dt plus L2 di by dt plus so on till Ln di by dt. So from here you can see the equivalent inductance is simply the sum of all the inductors in series. So this is similar to the resistance in series. Okay. Now what about parallel combination? In parallel combination, what is going to happen? The voltage is going to be the same across all of the inductors. The total current if you take as I, and each individual currents we will take as I1, I2 and so on till In. Okay. And this inductor is L1, L2 and so on till Ln. So now if you apply KCL here, then I is equal to I1 plus I2 plus so on till In. Now what is I? This is 1 by L equivalent integration of the voltage across it, and this is equal to 1 by L1 VDT plus 1 by L2 VDT plus so on till 1 by Ln VDT. So here you are going to get an equation which is similar to that we saw in the parallel resistance. So on till 1 by Ln. Okay. Now a few important shortcuts that you need to remember when two inductors are in parallel. Then what will be the equivalent inductance? L equivalent is equal to L1 L2 by L1 plus L2. Okay. Next, what about inductors which are having equal inductances? Okay, let's say there are n number. Then L equivalent is equal to n times L. And what about parallel inductances? Here L equivalent is equal to L by